The title of this presentation is the Replicator Dynamics of Generalized Nash Games. And this was a project I worked with Monica on back when she was my thesis advisor. It's a nifty little result that tries to connect the dynamics of generalized Nash games to that of evolutionary games. And so I'll start with a quick background on both of those. So the generalized Nash game, the GNEP, the Generalized Nash Equilibrium problem, is characterized by a finite set of players where each player controls a finite vector of variables and they're trying to optimize their objective function subject to constraints. And the key distinguishing feature of generalized Nash games is that this constraint set depends on variables outside that player's control. The actions of your opponent somehow constrain the choices available to you. So a very trivial example of this would be like a two-player game where each player picks a positive integer, and the constraint is that the sum of these positive integers must be even. So if your opponent picks an odd number, you must then also pick an odd number. And so you have to adhere to the constraint imposed by your opponent's action. However, you're not prescient. You don't actually know what your opponent's going to do in advance. You have to adhere to the constraint of what they do and at the same time not exactly know what they're going to do. So it's a little bizarre, but it's proved to be a very powerful modeling tool, especially in economics and the engineering literature. So here's the general form. Again, a finite list of players that each controls certain variables, and the key distinguishing feature is that the constraint set depends on variables not under their control. So it turns out that if we subject everyone to an identical constraint set, the problem becomes a lot easier to deal with. And we call this a GNSC, a generalized Nash game with shared constraints. And I'll just show you an example. I'll give you our assumptions first. So in this presentation, we are working with GNSCs with the following additional assumptions. We assume that K is a non-empty bounded convex polytope, and we assume that all of the objective functions are convex with respect to the variables under that player's control, and has a Lipschitz continuous gradient. Now, this assumption is, relatively standard. However, this one is not. Ideally, we'd like to be able to say something is true on an arbitrary convex set. But as it stands, the formulation we created is so fundamentally intertwined with the notion of vertices and edges that we weren't able to do that, although I believe that might be a worthwhile future line of inquiry. So here's an example of a GNSC, a very, very simple example of a GNSC. And again, the key distinguishing feature that makes it a generalized Nash game is that, this constraint set of player who controls variable X is dependent on Y, which is a variable under control of player 2. And what makes it a GNSC is that these are the same. These constraints are identical between the two players, except of course the ones, X less than or equal to 0 doesn't appear under player 2's constraints. You could technically throw it under there and it wouldn't affect much, but for notational simplicity, you typically omit that. So here's an example of a GN that isn't a GNSC. And again, so in this case we have, it's not showing it, but there. The general solution to this one is just this line segment. And then in this case we have a GNSC where the constraints aren't identical, and that's essentially all there is to it. And then the general solution to this is just the point 1, 0. And this is typical that you get larger solution sets with GNSCs because the points that are most conducive to being Nash equilibrium are on the intersection of the relative boundaries of each player's constraint set. And since all those sets are identical in a GNSC, the relative boundaries coincide. So you can tend to get these larger solution sets, but in general, GNSCs are much easier to deal with. And so evolutionary games, on the other hand, so in the very simplest case, it's a two-player matrix game where each player has a choice among n pure strategies, and there's a payoff matrix, essentially. It's very, very simple. And then all strategies must belong, they're probability vectors, essentially. they all must sum to 1 because these are used to represent proportions of some population adopting some certain strategy. So they all have to add up to 1. So they belong to this simplex here. So the dynamics of the evolutionary game can be described using something that's known as the Replicator Equation, which is a fairly simple differential equation. What we have here is, so essentially it takes your strategy. So the goal, I guess I didn't mention this, the goal of an evolutionary game is to find the strategy that is the best answer to itself. Any strategy which is the best answer to itself is a Nash equilibrium of the evolutionary game. And so what the replicator equation essentially does is it says, well, is pure strategy 1 outperforming your strategy? If so, increase the amount of x1 you have. Is pure strategy 2 outperforming your strategy? Then increase the amount of x2, and so on and so forth. And so what we end up with is the Folk theorem of evolutionary game theory that states that every stable solution to this system is a Nash equilibrium of the associated evolutionary game. And Nash equilibrium is defined, as I said, any strategy that is the best answer to itself. So what we did is we tried to build a bridge between these two types of games. And because generalized Nash games are so broad, we tackled this from the angle of trying to express our population game as a generalized Nash game. And we were successful in doing this. So this is the 2-player case, the very simplest example. And essentially what we've done here is we have player 1 is trying to find the strategy X that performs best against Y. And player 1 prime is just a shadow player that ensures at any Nash equilibrium X equals Y. So in other words, X finds the best strategy against X. For if it was not X, then player 1 prime would not be at their, they could find a smaller value for their objective function. And if there was some strategy better against X than itself, then player 1 would not be at their ideal strategy. And so the solutions of this generalized Nash game coincide with the solutions of the associated evolutionary game. And so we had the replicator equation to describe the dynamics of our evolutionary game. With generalized Nash games, we have something called the projected dynamical system. And it shares some of its, a GNSC shares some of its solutions with the projected dynamical system. Essentially what it does is at every point, the slope is equal to the Gateau derivative at that point in the direction of the negative gradient of the objective function. And it equates to projecting onto the tangent cone at any given point in the constraint set. You take the negative gradient and project it onto the tangent cone of the constraint set. And so it's known that some of the rest points of the projected dynamical system are solutions to the associated GNSC. And so the projected dynamical system associated to the GNSC we created for our evolutionary game looks like this. And so the question is, how do we link these two dynamics? How do we link the projected dynamical system to the replicator equation? And first, we can just observe how they look. So the projected dynamical system, it gets to the boundary and then it immediately starts projecting onto that boundary, and it ultimately converges to its rest point, which is a solution known as the variational equilibria of our GNSC. The replicator equation, it does the same thing, but it kind of does it more gradually. It sort of slowly coerces itself into the tangent cone as it approaches the rest point, and it slows down considerably as it gets nearer and nearer. The other notable feature about the replicator equation is that all vertices are rest points, regardless, and the vertices that happen to be stable solutions to the system correspond to Nash equilibria, and we ignore the ones that aren't stable. But it's necessarily the case that every vertice becomes a rest point of this system. So with a little bit of algebra and sort of in the spirit of what we're seeing here, which is that it sort of slowly projects onto each edge, we can rewrite the replicator equation in the following equivalent way. And again, this is just algebra and rearranging terms, but it's inspired by that image. And essentially what we have is that our AX projects onto the edge, and we have it sort of projecting a little onto each edge at all times via this summation term. EI and EJ are just coordinates of two adjacent vertices on the simplex. These terms out front ensure that once it actually arrives at the boundary, all the other summands go to 0, so that it's only projecting onto this boundary and it never exit or escapes the constraint set. And so in the spirit of this process, we thought we'd try and do this in a more general case, not just in the case of evolutionary games, but for GNSCs in general. So we're starting with a PDS, and we want to find the replicator dynamics associated to this projected dynamical system. And we have some, Lipschitz function negative f of x. And so we start by taking the half space representation. And again, we assume that K is a convex bounded polytope, not a standard assumption, but one we're making. And so K has some half space representation where GI are affine functions that define the planes essentially that we're working with. And it has a vertex representation. We can number them. And for each pair of adjacent vertices, we can find a subset of this half space representation of K where each element Hij is composed of the functions that are somewhere positive on the line connecting I and J. So in other words, we want to multiply this function, the half space representation of this edge here, by these two summands, so that when it arrives at this boundary here, these zero out and it doesn't end up projecting out of the shape. We don't want it to leave the constraint space. So we take these half space functions and we multiply them together and mirror the replicator equation. We can relax this system by considering the following classical dynamical system, which here is just, we've explicitly written out the projection. This is just the projection onto the line connecting these two vertices, Vy and Vj. And this Gijx, again, is just this function here that ensures that all the other summands go to 0 when it hits one of the edges of interest. And so a theorem that we showed in our work is that the stable rest points of this generalized replicator equation are in fact rest points of our original projected dynamical system. And the proof is long and tedious, but it essentially relies on the fact that if it's not a solution to this, then it cannot be, it's not in the normal cone, so it projects positively away from the rest point in some way, shape, or form, and it contradicts stability. So we prove the contrapositive, essentially, of this theorem. So here's an example. The example from earlier, it's very, very trivial. So we have a GNSC here, 2 players. Obviously, he wants to go to 2, he wants to go to 3, and they're subject to these constraints. And this is a GNSC with global constraints set this, and it shares some of its solutions with the following projected dynamical system. And so the vertex representation of K is this, the half space representation is this. And so we can relax our system as we did before to get this. This is essentially exactly as I described. We take these half space representations, multiply them out front, take the lines connecting these vertices, sum it all up, and this is what we get. And this is we can call this, if you will, the replicator dynamics associated to our GNSC. And this GNSC doesn't correspond to any particular evolutionary game, it's just a GNSC. And the only stable rest point is 0, 1, which does indeed correspond to a solution of the original game, but just one of them. So I guess the next steps logically for this would be to extend it past a polytope and to show that it applies to a general convex set. That would be a definite angle you could go at. Another way you could go is adapting this method so that it applies to the much broader class of generalized Nash games, because we're dealing with GNSCs here, but there might be large theoretical obstacles to that. It's hard to say. I haven't looked into it that much, to be honest. And yeah, there's some references, and thank you for listening. And if you have any questions, let me know.
Perfect, thank you, Jason. So if you have any questions, please give your name in the chat or ask the question. So in the meantime, Jason, I was wondering whether you tried some more complicated problems already, or?
Yeah, so I tried. I tried a multiplayer evolutionary game, a multi-species rather evolutionary game, where you have 2 different species, and each of them has their own sort of proportion associated to them, so they each belong to their own simplex. So that would be one of the more complicated games I've successfully used this on.
Okay, interesting.
I think, Jason, I wanted to bring you back to one of your slides, because you said we were looking at this problem from the perspective of the Folk's theorem. Have we concluded anything about this Folk's theorem? Because we started with it, and I think maybe we switched ourselves along the way.
Yeah, so we successfully generalized part 2 of the Folk theorem, which says that any stable solution of this is a Nash equilibrium, and we generalize this to GNSCs so that any stable solution of our generalized replicator equation is a solution to the associated game. However, part 3 of the Folk theorem, which says that every an asymptotically stable solution evolves to a strict Nash equilibrium, we have not addressed that. So that is an open question, and that would have been a good thing, I guess, to include on the next step slide, is generalizing that aspect of the Folk theorem. We did not touch that, you're correct.